So every physical and chemical process we were talking about yesterday involves energy transfer of some sort. So um, when we have a physical and chemical change, you can see that energy in terms of heat or light. For instance, when we light the Bunsen burners, we have to provide a spark, basically. And if you remember, we watched the thermite reaction in class. There was a lot of heat and light given off there, and to get the reaction going, the guy had to put the sparkler in there to get it to start. So sometimes we have to put energy into a reaction to get it started, and sometimes energy is given off. So some reactions we look at are going to be cold. Some reactions we look at are going to be hot to the touch. It just all depends on whether energy is being sucked out from the environment or put back into the environment. But in either case, we call that the law of conservation of energy, that energy can't be created or destroyed. It's just exchanged between the environment and the reaction, or vice versa. So what we're going to do today is we're going to classify matter into several types. And for now, I have this chart here. We're going to break down each part individually. But the first thing we want to ask about matter is, can it be separated? If the answer is no, that's what we've been talking about, pure substances. We've had sugar, sucrose, water, and we burned the sugar to break it down into carbon and water, and then we broke the water down into hydrogen and oxygen. So things that can be broken down by chemical means, those are compounds. But things that can't be broken down, like gold, aluminum, anything that can be found on the periodic table, those are all elements. Today we're going to be talking about mixtures. So we have to ask ourselves, is the composition uniform? If it's yes, we call that a homogeneous mixture. So like air, sugar, and water. So like a lemonade or Kool-Aid. Stainless steel is actually a mixture. It's a certain percent of like iron and other elements. Those are all mixtures that are spread evenly throughout. But heterogeneous mixtures would be uneven. Like if you had granite or wood, sometimes you get like a knot in the wood. It's not always even throughout. Blood sounds like it would be a homogeneous mixture, but it's actually not. Blood, it has a lot of like platelets in certain places and red and white blood cells. So if I get a sample of blood from one location or one person, it might be different from another location. So we're going to look at, we got plenty of examples. If you're still wondering the difference between the mixtures there, we've got plenty of examples to look at. But this is just kind of an overall view of everything. So just to look at it at the molecular level, again, if I only have one type of atom, it's an element. If I have multiple types of atoms, it's a compound. If it's a mixture, that means I have more than one type of atom or molecule. If it's homogeneous, it's uniform in composition. If it's heterogeneous, it's not uniform. So let's define a mixture. A mixture is a blend of two or more kinds of matter. And the key here is they each retain their own identity and properties. So when I mix sugar and water, like the water's still like watery, it's still liquid, and the sugar is still sugary. It makes the water sweet. So the sugar and the water each still have their own properties. That's why they're a mixture. On the other hand, sodium is a very like reactive metal, and chlorine is a toxic gas. When I put those two things together, they're completely different. They turn into something brand new they turn into sodium chloride, which is table salt. But if I mix salt and water, then we have a mixture. And if I mix the salt and water well, it's going to be homogeneous, and we call that a solution.
Riley, welcome to the office.
So again, mixtures can be separated physically. Homogeneous means they're uniform throughout. So in other words, if I take a sample, like if I had a jar of Kool-Aid, if I mixed it well enough, the first cup I pour out should taste just the same as the last cup. But if I have something like heterogeneous, like a clay water mixture, the first glass I pour out of the pitcher is not going to be like the last glass because there's going to be a lot more clay. Same with sand. Sand doesn't mix well. So we see on the next page here. I guess I have a question here before we get to that. But so here's the slide with the sand and water. You can see it settles to the bottom, does not mix well. Whereas sugar and water, a homogeneous mixture, does mix well. And let me just show you too at the molecular level. You see how the sugar is mixed within the water molecules, whereas on the right, the sand, the silicon dioxide, settles below the water molecules. So like I said, I've got a ton of examples for you. More homogeneous mixtures, iced tea, because you have that uniform distribution. Stainless steel, hopefully one part of the steel is the same as all the other parts of the steel. Maple syrup is mixed evenly throughout. Now, orange juice is debatable. Apparently, the person who made this chart likes to chew their orange juice because they're putting it in the heterogeneous camp. Personally, I like orange juice more without the pulp, so if it's, concentrated enough, it could be homogeneous. But those things, you have an uneven distribution. I can see tomato sauce for sure. You've got especially if you've got a lot of components in the tomato sauce, like onions, peppers mixed unevenly throughout. Chocolate chip cookie, you can imagine the dough. If you and your friend had a cookie apiece, what's the chances you're going to get exactly the same number of chocolate chips? So that's something that's going to be uneven. And obviously you have the doughy part and the chocolate chip part. Granite and salad are also two more examples. Salad obviously can be easily separated with your fork. You've got the tomatoes, lettuce, etc. So those are some examples of heterogeneous mixtures. So here's another question. A compound differs from a mixture in that and then we have another one. 3 of the following must contain 2 or more kinds of atoms. Which one does not contain 2 or more kinds? So classification of matter. We're going to continue with pure substances. Again, if you think back to that chart, if you want to go back and refer to that, a pure substance can either be a compound or an element. So with pure substances, every given sample has the exact same characteristic or properties. So with water, we said that water was a pure substance. Water is a compound, and it's always going to have that same composition: 11.2% hydrogen and 88.8% oxygen. Now, this might be confusing. If you remember, we looked at the electrolysis yesterday and saw the bubbles forming, and we said that there was twice as much hydrogen and as oxygen. So kind of think about why this might be. We're going to learn later the reason, but think about how can I have the mass be 88% oxygen when we saw yesterday that the volume was twice as much hydrogen as there was oxygen. Kind of leave that a mystery for now. So the last thing we want to talk about with this section, they throw it in here, is about the purity of the chemicals. And we might assume something is totally pure, but there's different grades. There's different grades for food standards and lab standards. You might see the level of purity be different for what we order in the lab here at, in our district versus what you might go buy at Walmart. We might have the same chemicals, but the level of purity is different. And same with, we have a water distiller in our lab that's going to remove a lot of impurities, but it's probably not going to be to the level that you would see like in an industrial lab that makes distilled water for distribution. So pure, to an extent, is not perfectly pure. Like the stuff we deal with in lab is not going to be 100% pure, but we do the best we can. So we're going to stop here. There's the assignment for tonight's a little bit lengthier than normal, so hopefully we can finish that. And if you have any questions, let me know.